Okay, in this video we're going to look at function operations. So we'll look at addition, subtraction, multiplication, division, and then a final one called composition. And so for functions f of x and g of x, the notation for addition is parentheses f plus g, close parentheses, and then parentheses x is equal to f of x plus g of x, and then very similar for subtraction, multiplication, and division. So one thing to be a little bit careful of, usually parentheses means multiplication, so we do not want to do a distributive property here, so it's not distributive property. That's just the notation. And so we can always add the functions provided that we're in the domain of both f and g. If we're doing the division, then g of x cannot be 0. And then for composition, f composed with g of x, the fog, that is f of g of x. G of x is going to be the inner function, and so provided that g of x is in the domain of f when we do that composition, make sure that composition is actually valid there. So we'll go through, do a couple examples of each. So let's go ahead and get started. Alright, so first thing we're going to do is we're going to be given three functions, and we're going to do a couple of different operations. One will be generically the equation, and then there'll be some specific ones where we're evaluating some sort of function operation. So there's our three functions, and part one says, okay, let's do f minus g of x. This is the one where most folks are going to make an error. This is f of x minus the entirety of the g of x formula. So I put those extra parentheses there to help remind myself that it's the entire g of x that's being subtracted. So f of x is the x squared plus 5x plus 6, and then minus the x minus 9. So usually what happens is, we'll subtract x and subtract 9 as opposed to subtract x and add 9 because we forget to distribute that minus sign. So we get x squared plus 5x plus 6, and then minus x and plus 9. We'll go ahead and combine like terms. Alright, so there's combining like terms, and then we have to resist the temptation to solve this. We are not solving it, so don't set it equal to 0, don't factor it, don't use the quadratic formula, don't do any of that. That's it. That's the formula we've simplified. Now, we can also talk about the domain of this thing. Both f and g are polynomials, which means they don't have any square roots or denominators with a variable in the denominator. So that means that the domain is going to be all real numbers. Okay, there is no restrictions. And this is not a composition, sorry. It's just a domain. Domain, I guess we could say, of the subtraction of the functions, but we'll just say the domain. It is not a composition. Number 2, f minus g of 3. So I have actually two possibilities. I could plug 3 into my formula I just found, or I can do it following the definition, which would be f of 3 minus g of 3. So we'll plug 3 into f and plug 3 into g, find what those values are, and then take their difference. So again, we need those parentheses around the g of 3 so that we make sure we evaluate it correctly. Okay, so we get 9 plus 15 plus 6, and then minus negative 6. I think that's all going to end up being 30 plus 6, or 36. Okay, or I can use my formula, f minus g of 3 was the formula we came up with generically. So that'd be 3 squared plus 4 times 3 plus 15, and that will happen to be 36 as well. 9 plus 12 and plus 15, so that will be 36 as well. So if I know the generic formula like I have there, then I can use that to evaluate multiple values as needed. Well, as needed, I guess, if they ask us to. Anyways, let's go on and look at another one. So it's going to be the same function, so I'm going to write them real fast. Okay, so now we're going to look at division. We're going to look at f divided by h of x. So that's going to be the formula for f divided by the formula for h. And the top is going to be the x squared plus 5x plus 6. And the denominator is going to be the square root of x plus 3. And we get the best of both worlds. Not only do we have a denominator, but we have a square root. So normally what we would do with the radical, that's the thing underneath the square root, is we'd set that greater than or equal to 0. Now the problem is it's in the denominator, so we don't want to it to be 0, so we set it strictly greater than 0, and so that's going to give us x is greater than minus 3 as our domain. Okay, so x plus 3 must be greater than 0, so x is greater than negative 3. So then our domain, hopefully I didn't write composition this time. Okay, good. Alright, so it's not a composition here either. Doesn't have the little composition circles. Alright, so that's our domain. Number 4, let's find f divided by h of negative 2. So I could use my formula, or the formula is essentially just evaluating the top and the bottom at negative 2 anyways. So we'll stick negative 2 into the f function and into the h function, and we'll evaluate. So negative 2 quantity squared plus 5 times negative 2, and plus 6, all over negative 2 plus 3 under that square root. And simplifying the top there, that's going to be 0 over the square root of 1, and that's going to be 0. Okay, and that is it for that one there. I think we're going to move on to another screen here, and we're going to rewrite the same functions, and this time we're going to do f times g. So it's a little bit different than composition. Composition will look like this. Okay, that's composition. Sometimes with multiplication they'll put the multiplication dot. So we have to be a little bit careful. So if you got that circle there, that's composition. If it's just a little dot, that's multiplication. Or like in number 5 here, you don't see anything there. That's what's called implied multiplication. So if I stick f and g next to each other with no operation in between them, the understood operation or the implied operation is multiplication. With composition, you will always have that big open circle. Alright, so we're going to find f times g of x, so that's going to multiply the formula for f times the formula for g, and that amounts to multiplying two polynomials together. Okay, so x squared plus 5x plus 6, and then x minus 9, and so we'll have to do the distributive property, distribute that x squared, distribute that 5x, and distribute that 6. And then we'll combine like terms. And then we're going to pause for a second. So remember, we're not solving it. We weren't asked to solve it anywhere. So don't set it equal to 0. Don't try to factor it. It's not even a quadratic, so we couldn't use the quadratic formula. So that's it. They might ask us for the domain. What we did was we multiplied two polynomials together. Polynomials do not have square roots, and they do not have variables in the denominator. So we're good. The domain is all real numbers. Okay. Now number 6, we're going to find f times g of 2. So we could use our formula we just came up with, or we can follow the definition and say, okay, well this is f of 2 times g of 2. And so we'll plug 2 into f, so that'll be 2 squared plus 5 times 2 plus 6. And then 2 minus 9. So that's going to give us 20 times negative 7, and I think that's going to be negative 140 there. Okay, so those are what I would consider kind of maybe the easier of the function operations. Those certainly you should have seen before in an Algebra 1 class. Maybe you took, our Math 0306 or Math 0314. You would have seen those type of things. We're going to look at composition, and before we do composition, like the one function into the other, we're going to do composition off of two graphs, and then we'll also look at a table here. So composition is feeding one function into another. And so here we have f and g. Okay, so I did my best to take pictures of what you got on the notes, so you'll have something kind of similar to this on the homework. Okay, so there's your F, there's your G, and we're just going to go through, and well, we're not going to quite do composition yet. We're going to get there. It's coming. Don't worry. So F plus G of 2. Okay, so that's going to be F of 2 plus G of 2. So F of 2 is the Y value when X is 2. So that looks like negative 2. And G of 2 is 0. And so we add those values and we get negative 2. Okay. Alright, now if we do F minus G of 4, that is going to be F of 4 and minus G of 4. F of 4 is 2 and G of 4 is 2. 2 minus 2 is 0. Okay, how about F times G of 3? So that's going to be F of 3 and times G of 3. F of 3 is 0. G of 3 is 1. 0 times 1 is 0. Okay, how about F divided by G of negative 4? So that's going to be F of minus 4 over G of minus 4. So F of minus 4 is 0. G of minus 4 is 2. So 0 divided by 2 is going to be 0. Okay. Now we get into the composition. So F composed with G of X of, well, I guess we're doing F composed of G of minus 2 here. So this is rewritten as F of G of minus 2. Okay. So we're going to go find minus 2. G of minus 2. So G of minus 2 is 0. So we're going to replace G of minus 2 with 0. So that's going to be F of 0. And so F of 0 is 2. Alright. How about G of F of 2? G of F of 2. So we're going to go find F of 2. F of 2 is minus 2. And then we're going to go find G of minus 2, which happens to be 0. Alright, how about F of negative 4? That is F of negative 4. F of negative 4 is 0. F of 0 is 2. Alright, and then of course we'll do G of 3, which is G of 3. G of 3 is 1, and G of 1 is 1. Okay. Alright. So that is composition, doing it off of two different graphs. We also did a little bit of the other operations, addition, subtraction, multiplication, and division. Now we're going to exclusively look at composition for the rest of the notes here. So that was what I was most excited about doing, was doing that composition. Okay, so we're going to look at a table now. So here's your table. You got your x values in the left column, f of x in the middle column, and g of x in the right column. And then we have a couple of different things we're going to evaluate. So problem number 15 from the notes will be f of g of 7. So the x value is 7, and so we're going to find g of 7. So g of 7 is 5, okay? So g of 7 is 5, so we can replace the g of 7 with 5. So that becomes f of 5. Okay, now 5 is your input, that's your x, so we go to 5. And then what is f of 5? It's 8. Okay, then we get to play the same game again. Now we're going to do g of f of 4. So we're going to find the x value of 4. And then we're going to find f of 4, which is 5. And we're going to replace f of 4 with 5. G of 5. Now 5 is the input, that's our x. We're going to find g of 5, which is 0. Alright, play the same game again. Let's do f of 5. So we're going to find 5 on the x. And then we're going to find f of 5. F of 5 is 8. So this becomes f of 8. We'll go find 8. F of 8 is 0. Okay. And finally, we'll find g of 3. there's 3. G of 3 is 3. And we're going to find G of 3 again, which happens to be 3 again. Okay? And so that is our real basic examples of composition. Later on, if we're getting into pre-cal, we might want to know what kind of an inside function and an outside function is. So, for example, if I looked at like x minus 2 squared, I could say that the inner function is x minus 2, and the outer function would be square, and this x here would stand for our input. So this function would take input and square it, so if we fed it x minus 2, then it would square the input, and that would be a composition of two functions. And so we run into that a bunch in calculus, and one of the key skills there is being able to realize what is the inside function and what is the outside function. If we can't recognize that, then it's very difficult to do some of the calculus because of the algebra that we're covering right now. All right, so if we're looking at finding, the composition, you can think of it as maybe like a leapfrogging or something like that. So maybe, over here that's the domain of G, and then we're going to take an X there, and then we're going to send that over, and that's going to live in the domain of F, and so there's G of X. And so G takes it that way, and then we're going to take a function f, and that's going to take it to its final destination. So some sort of like connecting flights or something like that. So f's going to take it here, and that's the final destination. So we got to make sure that the domains line up correctly, and so we'll be suspicious if we see denominators and square roots. So if I don't see any of that, then the domain is everything for that composition. Difference quotient is also an application of a composition. So anyways, let's go ahead and let's do some examples of composition. And the first thing we'll need to do is talk about the how to kind of go about finding the domain of the composition. Okay. So if I'm going to find the domain of a composition of functions, what you're going to do is you're going to find the domain of the inner function, and so you're just looking for denominators or square roots. Then you're going to find the domain of the quote-unquote answer, and that's going to be what the composition is after we simplify it. The intersection of the inner function and your composition formula, that's going to be the domain of the composition. And so there's a silly joke in here. So when you're looking for the domain of a composition, you're going to find the dinner and the dancer. So if you're looking for the domain of the composition, you're looking for dinner and a dancer. I know it's a terrible math joke. Anyways, so we're going to go ahead and play with a couple of functions here. I think we got like, 6 or something, 5 or 6. And we'll do a couple compositions and find the domain of each of them. So here we go. So given all these functions, okay. So given f of x is x squared plus 2x plus 3, g of x is x minus 2. So both f and g, they don't have any problems. So if I only have f and g involved, the domains could be everything. They're both polynomials. H of x is x over x plus 9. K of x is 1 over x minus 4. So if I'm involving h or k, I do have a denominator, so I've got to worry about dividing by 0. So that'll have some sort of restriction. And then m of x, which is the square root of x minus 4, that will also have some sort of restriction because of the square root there. Okay, so we're going to go ahead and we're going to find, what are we going to find? Find the composition. Okay, what are we going to, and the domain. So we're going to do f composed with g of x, okay? So that is f of g of x, and g of x is your inner function, which happens to be x minus 2. No denominators, no roots, no problems, so the domain is going to be everything. Okay, now here's what f does. F takes inputs, whatever it may be, and it squares your input. Then it adds 2 times the input, and then it adds 3. I don't know why I'm writing on diagonal, but I am. Okay, so if your input happened to be, for instance, x minus 2, you would replace all the inputs with x minus 2. Okay, so that's what the function does. X in the formula f of x equals x squared plus 2x plus 3. The x stands for the input. Okay, so the input is going to be g of x, and g of x is x minus 2. Okay, so f of x minus 2. So it is going to be input squared plus 2 times input, and then plus 3. So foiling x minus 2 times x minus 2 will give us x squared minus 4x plus 4. Distribute the 2, 2x minus 4 plus 3, and then combine like terms. Okay, and stop there. We're not solving it. Don't set it equal to 0. We got to resist that temptation there. Okay, so that's the composition formula. It is a polynomial. It does not have any restrictions. That's your composition, so no new restrictions. And so the domain of your composition is going to be the intersection of the two, the inner and your answer, and they both are all real numbers. So the domain of the composition is all real numbers. All real numbers. Okay, I don't think I have an example built into the notes, but let's do one of these just for fun, just to say that we have an example of doing this numerically. So let's say I have f composed with g of, I don't know, 1. Okay, so that's going to be f of g of 1. Okay, so if I find g of 1 is going to be 1 minus 2, which is going to be negative 1. Okay, so that's going to be f of negative 1, which will be negative 1 squared plus 2 times minus 1 plus 3. So we get 1 minus 2 plus 3, so hopefully my arithmetic's okay. I think that's going to be 2. So in case they ask you a numerical evaluation of composition, that's what you do. You just plug in the number into the inner function, get that output, and then take that output and plug it into the next function as your input. Okay, we're going to look at, I think, 2 or 3 more of these compositions. We're going to be using the same functions here, and so I'm going to go ahead and write very fast all of those functions again. So there they are. And we're going to say find the composition and the domain. And this time we're going to compose m with g. So m composed with g. That will be m of g of x. G of x is going to be our inner function, which is our x minus 2. No denominator, no square roots, no problems for g, so that domain is everything. Okay, so g of x is x minus 2, so this is going to be m of x minus 2. So here's what m does. M takes your input, and it says, okay, here's your input. We're going to go ahead and subtract 4 from it, and then we're going to square root it. So if we're feeding it x minus 2, we're going to take an x minus 2, we're going to stick it right in there, and then subtract 4 from it, and then take the square root. Okay. So square root of x minus 2 is your input, minus 4, and so that's going to be x minus 6 under the square root. That is your composition formula. There's no more to do there. It does have a square root, and so you know what to do with square roots. Set the radical, not the radical, but the radicand. The radicand is what lives under the radical. Set that greater than or equal to 0. So that gives us x is greater than or equal to 6. Okay, so now we're going to look at these two. And so we have the domain of minus infinity to infinity for the inner function. Inner function doesn't care what you feed it. However, the composition does have some problems. The x must be greater than 6. So we have to roll with the more restrictive of the two. And so the domain of our composition is going to be 6 to infinity, including 6. Okay. And so you might be wondering, well, we kind of solved something at the end of this one, and that's because we had a restriction in our domain. So if we looked back at the previous one, we had some sort of polynomial. We had x squared minus 2x plus 3. That was our composition. there was no restrictions, so we didn't have to do anything else. This one we did because we had a square root involved, so we had to figure out what the restriction was. All right, what do we got? Two more. We're going to find h of k, so we'll write very fast all of this stuff again. So h of k of x is going to be h of k of x, and k of x is our inner function, and it does have a denominator. So we're going to take that denominator and set it not equal to 0, and we're going to go ahead and write down what our restriction is. So x minus 4 cannot be 0, so therefore x cannot be 4. Okay. Alright, so here we go. H of k is 1 over x minus 4. So here's what h does. H takes your input, and it says input over input plus 9. So where you see the inputs, you're going to be putting 1 over x minus 4. So it's going to look like kind of a crazy fraction here. It's called a complex fraction. So 1 over x minus 4 over 1 over x minus 4, and then plus 9. Okay. Now your common denominator here is x minus 4. So we're going to multiply the top and the bottom by x minus 4. We're going to clear that fraction there. So when we multiply the 1 over x minus 4 times x minus 4, the x minus 4s will absorb, and we'll be left with 1. On the bottom, we'll have one. We'll distribute. Okay. So when I do the 1 over x minus 4 times x minus 4, the x minus 4s will absorb, and we'll be left with 1. And then we'll have 9 times the quantity x minus 4. Okay, and we'll have to distribute and collect like terms. So we get 1 over 9x minus 35, and that's our composition formula. We do have a denominator, so we got to go figure out what our new restriction is. So we're going to take that denominator of 9x minus 35 and set that not equal to 0. And so that would be adding 35 and then dividing by 9. So 35 over 9 is the new restriction. Okay. Alright, so then if we're going to find the domain of the composition, we do have two restrictions. X cannot be 4 and x cannot be 35 over 9. So we can go ahead and put those on a number line, and then we got to hop over those two values, and that kind of helps us with the domain here. So minus infinity to 35 over 9, union 35 over 9 to 4, and then union 4 to infinity. And that would be the domain of our composition. Okay. We're going to look at one more. We're going to do h composed with itself. And we'll write really fast one more time. So h composed with itself. Okay, so that's going to be h of x. H of x is your inner function, and that is x over x plus 9. So it does have a denominator, so that means we're going to have a restriction. So we're going to set the x plus 9 not equal to 0, so x plus 9 not equal to 0, and so our restriction will be x cannot be negative 9. Okay. H of x over x plus 9, so that is going to be input divided by input plus 9. Okay. The common denominator here is x plus 9. So we're going to multiply the top and the bottom by x plus 9. Okay. X is going to be the remainder when we multiply x over x plus 9 times x plus 9. The x plus 9s will absorb. On the denominator, same thing goes here. X over x plus 9 times x plus 9. The x plus 9s absorb. We're left with x. And then plus 9 times x plus 9. Okay, and do not cancel those x's. They do not cancel. They will not cancel. So that would be kind of like, let's see. What can we do? Like 5 over 6. No, let's do, yeah, we could do 5 over 6. Is that equal to 5 over 5 plus 1, And then if the 5's cancel, what is this? So it's a mess. So we can't cancel those x's. We can only absorb or cancel factors if we're doing multiplication, everything's factored. So in this case, we're doing multiplication, or this is all factored out, which it is not. Okay, distribute the 9x, and we have 10x plus 81. We do have a new restriction because we have a denominator. And we'll go ahead and say 10x plus 81 cannot be 0. And to find that, we're going to subtract 81 and then divide by 10. Okay, so we have two restrictions we got to worry about. We got negative 9 and negative 81 over 10. So we'll do the same thing we did in the previous example, is we'll go ahead and draw our number line, and that just kind of helps us with the interval notation. So there's our number line. We got to hop over negative 9 and negative 81 over 10. Okay. And so our domain is going to be negative infinity to negative 9, union negative 9 to negative 81 over 10, and union negative 81 over 10 to infinity. And that would be our interval notation for the domain. Okay. So hopefully you found this helpful. A pretty brief review of addition, subtraction, multiplication, division of functions, and then a little bit of an introduction to function composition, and anyways, let's stop there.